Hey, my name is Branham Stefan, and today I'm going to be going over the Atlantic Data API that gives public access to both the U.S. current, historical, and the state current and historical COVID-19 case count. So, looking at the original US data, we can see some pretty high fluctuations early on. A lot of bias towards a 100% positive test rate, which would be maybe indicative of an extremely small sample size. Maybe those who only had COVID were testing for it. We can see a peak at 0 in the Parsons window, as well as 0.5 and some complex roots. Due to the extreme bias early on, I actually went ahead and took a filter of the US data set to kind of remove some of those early test records and get a little bit better representation of the sample itself. After doing that, we can see a peak at 0, but we've removed the peak at 0.5, and we have some complex root peaks there. Additionally, I transformed the axis to squeeze in the records. Squeeze in the scale of the records, and we can see that evident in the plot to the right. All assumptions were met for the US data, excluding the constant autocorrelation, which can be seen in the bottom left. We can see the first half versus the second half of records, which do not have constant behavior. To combat this, I actually performed a non-stationary transform of a unit root 1, which we can see evident in the the right top left plot versus the right bottom left plot. We can see after running an AIC analysis on that, we found an optimal p-value of 22 and a q of 1, and we saw a series of several complex roots which were actually utilized for creating those peaks between 0 and 0.5. Running a unit root transform rolling window ASC on everything, we can see that early on we had a great fit. Early on we had a poor fit, and later on we had a great fit, suggesting that the data kind of leveled out and we had more predictable data, and certainty probably also had to do with a larger sample size. On the left side, we see a 4-day forecast, and on the right side, we see an 8-day forecast. Looking at the Louisiana COVID data, we can see similar behavior, although quite not as extreme. We see wandering behavior indicated by the peak at 0 in the Parsons window. However, we don't see any peak at 0.5. All assumptions were met for the Louisiana COVID data. Whenever I ran an AIC of analysis, we found a p-value of 6 and q of 1 as the optimal values, and we can see on the plot below that the optimal, the roots of the optimal AIC format for the Louisiana COVID data. They're all complex, which would explain the peaks between 0 and 0.5. Running a rolling test ASC, we can see that early on we had a great fit. Early on we had a poor fit. Later on we had a great fit, which actually deviates a little bit over time, which might be due to a rising in test counts. On the plot to the left, we can see a 4-day forecast, and on the plot to the right, we can see an 8-day forecast. I think in order to improve our model, we can actually do some various transforms, try out some different square root transforms, or maybe doing an additional unit transform to see if maybe we get a better model fit there. Those are things I'm going to try in the next set.